Now let's take a look at the concept and measurement of curvature. Now these three graphs are actually portions of a circle. And which would you say is curved more? On the top one, if I am tracing this, my question is, so how much curve is there? How much change is there? And on this one, look at how I'm having to move my hand more. And this one, lots of curvature. You'll see the definition in just a moment. If we take this first one, here's a point, here is a tangent vector. The definition of curvature is how much does that tangent vector change if we go from one point to another along the curve. Well, it's hard to find that same distance on any of these other curves, so let's do something a little smaller. Suppose we take this distance, which is about this distance on this one, and which is probably the whole thing on this one. So on the first one, here is a tangent vector, and at this point, here is a tangent vector, and the question is, how much difference are there in those two tangent vectors? Here on the middle one is a tangent vector, and here is a tangent vector. What's the difference in those two? Here is a tangent vector, here is a tangent vector. How much difference in those two? Now, this is the definition of arc length from earlier in the section. And here is the arc length function. Remember, S is a function of t, and we find t as the upper limit of the integral. Now, in the previous PowerPoint for this section, we also saw that the derivative of this function defined as an integral is nothing more than the integrand. Now with that last formula in mind, let's see what the definition of curvature looks like. The definition of curvature starts with the magnitude of the rate of change of the unit tangent vector, that's the bold capital T, with respect to the arc length. And so how much does the unit tangent vector change compared to a particular change in the arc length? The symbol for curvature is the Greek letter kappa. Now, the definition of curvature, the magnitude of the change in the unit tangent vector to the change in the arc length, is easy to remember, but not easy to work with. I'll show you the not easy to work with part, because we're going to use this definition to find the curvature of a typical vector valued function. So, first order of business would be to re-parameterize the function in terms of the arc length. So we can do the derivative with respect to arc length. Now, since we did this in the last PowerPoint, I'm going to go through this a little bit quicker. To reparameterize it, we need to take the definition of the arc length function, use a dummy variable, do the derivative, the magnitude, and simplify, and then integrate that. And then solve for t. Take the original function, r of t, replace the t with this, and we have r written in terms of s. So we have reparameterized the function in terms of the arc length. So now we need to find the unit tangent vector. Now the unit tangent vector is the derivative of this divided by the magnitude of the derivative. Well, now that's convenient. The magnitude came out to be a 1. Don't count on that always happening. And so the unit tangent vector for r would simply be r prime of s. But we'll call that capital T. And of course we need to do the derivative of that with respect to s. The derivative of the 1 over 10, 1 over square root of 10, derivative of any constant is 0. The derivative of 3 over square root of 10 cosine s over square root of 10. If we copy down the 3 over 10, the derivative of cosine would be negative sine times the derivative of s over square root of 10, which would be 1 over square root of 10. And the square root of 10 and square root of 10 would give us just a 10. So anyway, there's the derivative with respect to s. We need the magnitude of that. And there's our curvature. Now, obviously, that's kind of a pain to do all the reparameterization. Now, I'm going to show you how to develop other versions of this formula. They're a little easier to compute with. You don't have to be able to do the development if you'll keep those formulas handy somewhere. But I thought you might be interested in seeing where they come from. So we're going to simply rewrite this expression by dividing top and bottom by dt. And remember that d capital T over dt is written as just t prime, capital T prime, the derivative of the unit tangent vector. And so we just did this earlier. The ds dt is the magnitude of r prime of t. So this is another version of the curvature formula that might serve us better than the first one. Notice to use this formula, we still have to find a unit tangent vector so that we can do its derivative and the magnitude of that. And that could be somewhat of a pain. Now we'll take this vector valued function r and use our newfound formula to find the curvature. So we'll start by finding the unit tangent vector. And there's our formula from previous section. We do the derivative of r. We do the magnitude of that to turn it into a unit vector. Now, I might just point out we get kind of fortunate in this problem that our magnitude actually comes out to be just a 4. But still, it's the same idea, just may be a little uglier in the future. So there's our unit tangent vector. And in the formula, we need the derivative of that, and then its magnitude. Now again, we're just kind of fortunate that this one came out to be just a 1. But in our formula, we've got the magnitude of t prime. We just found that to be a 1. We've got the magnitude of r prime, which we found earlier to be the 4. And so there's our answer, regardless of the value of t. Now, since the unit tangent vector is r prime divided by the magnitude of r prime, we can write r prime as the magnitude of r prime times t. Now, we just did this a few minutes ago. ds dt is the same as the magnitude of r prime. So we can rewrite r prime as ds dt times capital T, the unit tangent vector. Now we're going to do the derivative of that according to the product rule. And again, I won't go through all the details of this. You can pause and look it over if you don't understand how to do that derivative by the product rule. And we're going to take the r prime and r double prime and do their cross product. Now again, that's kind of a pain, so I'm going to skip all the mechanics of doing the cross product of that and hope that you accept that we can do that. Here's the rules from the properties of cross product that I'm using. We're going to simplify this expression by using more properties from the cross product. And then a couple of observations. Now, we've done this before. What is t cross t? Any vector crossed with itself. That would be the zero vector. Well, since that's the zero vector, we can totally eliminate this term and have only the second term. So what we're wanting to take a look at here is actually the magnitude of r prime cross r double prime. So we'll do the magnitude of both sides of this equation. And we want to investigate a little bit more this t cross t prime, or more appropriately, the magnitude of that. Now, since a vector that is constant and its derivative are orthogonal, that means they intersect at 90 degrees. And we can write the magnitude of t cross t prime as the magnitude of the magnitude of the t prime, and the sine of 90 degrees. Since they're orthogonal, that's 90 degrees. Now, the magnitude of t is a unit tangent vector, is a 1. Sine of 90 degrees is a 1. So the magnitude of t cross t prime is the same as just the magnitude of t prime. So replacing the magnitude of t cross t prime with just the magnitude of t prime, we get this. And we want to solve for the magnitude of the t prime. So dividing both sides by ds dt squared, we get this. And remember, ds dt is the magnitude of r prime. Substituting, we get this for the magnitude of t prime. Now, all that work is so we could rewrite the first equation. So here was the first equation, kappa, magnitude of t prime. What are we going to use instead of magnitude of t prime? That's stuff we just came up with. Simplifying that, we get this expression. So that is our third definition for curvature. Now, I like this one. Well, probably because it's easy to program on the calculator. But this one has everything in terms of just r and its derivatives. So you can just take r, do its derivative and its second derivative, and then stick them together here, and you've got curvature. You don't have to do any reparameterization, and you don't have to find any unit tangent vectors. In motion problems, we've always used the v, which is the change or the derivative of r with respect to time, dr dt, which is velocity. And then the second derivative of r is the acceleration. So this formula is just another version of the formula that we just found, just using different letters. So this makes it very easy to put into a calculator. You can see on my program for the TI-89, I've called this curvature, CURV, of a vector function. And then the vector function would be given in parentheses when we call the program. So we're going to use, like in our formula, a v and an a. We do the derivative of r, store that in v. We do the derivative of v, store that in a. And then we do the cross product of v and a. That's the top. Take the magnitude of that. We do the norm of just the v vector, the magnitude, and raise it to the third power and divide. So there's one program that does the entire curvature calculations. Here's what it would look like. And you see we get the same answer. This is the problem that we did earlier. So let's take this curvature formula and see what would happen if we had y as a function of x. We could parameterize y equals f of x by choosing the x component to just be an x, and that would make the y component whatever the f of x is, the function. And since we're doing the cross product, and this is two-dimensional, we'll use a 0 for our k component. So using this as r, let's see what our curvature formula then would look like. If we do the derivative of r, and then the second derivative, we can use a cross product determinant to find r prime cross r double prime. So this would be the cross product of r prime and r double prime. And as you can see, the magnitude of that is going to be 0 squared plus 0 squared plus f double prime squared, all added up, and then the square root of that. And the square root of f double prime squared is f double prime. Except we got to make it positive because square roots don't come out negative. Then the magnitude of r prime would be 1 squared plus f prime squared plus 0 squared. So that would give us a new curvature formula, which we can simplify to this. So to find the curvature from the formula that we just came up with, we need to do the derivative of 3x squared minus 2x plus 4, and then the derivative of that, and plug them into the formula. Now, before we go to trying to do all of this, we can go ahead and plug in our value of x and then do the calculation. Of course, one of the good things about the formula is it lends itself well to putting into a TI-89. So I have called this program CURV FUNC. Remember the other one we did was CURV VECT. So that was when we had a vector valued function. Now what we need to put beside it is a function of x. So you can see again what's going on here is just a reflection of the formula we just came up with. We take f, we do its derivative, store that in dy. We do its second derivative, store that in d2y. We do the absolute value of the second derivative. We do 1 plus the first derivative squared, raise all of that to the 3/2 power, and divide. Anyway, that comes out looking like this. And you see we get the same answer as before. This page is just a summary of all the different versions of the curvature formula that we took a look at in the previous stuff in the video. And all of these are based on vector valued functions, and this other one is the only one we have for y as a function of x.